All right, guys. I want to talk about the power reducing formulas. Okay. I think those are the last set of questions that you guys are maybe not. I think you can do them without the instruction, but maybe you're hesitant to start them because we haven't talked about them. So I think you're going to find out that you're probably more than capable of doing those things here in a moment. What I want to do here is just show you, like, if I have sine squared of x, looks like that, right? Okay. Now, if I end up with 1 minus cosine of 2x all over, so those look the same, right? Or somewhat the same. But what is different about that red one? It's twice as high. So let's undo that multiple of 2 by dividing by 2. And we get the same curve, right? Okay. Right there, that relation to sine squared x is equal to 1 minus cosine 2x over 2. That is what we call our power reducing formula for sine squared. Okay. Because now the power reducing, meaning we had a power of 2 in our trig function in the green one, right? We have now a power of 1 in our trig function for the red one. That's what we're trying to do with power reducing. Now, when we do the power reducing, the trade-off or the cost of that is that we now generate an argument that is twice as big, right? 2x instead of 1x. So that might be something that we kind of have to work with, maybe analyze a little bit as we move on into some equations, if we do choose in those equations to make these substitutions. Okay? Yes?
So for the ones that are like cosine fourth, we're just breaking it into cosine squared times cosine squared.
Yes. Yes. So, and to answer that question, think about this. Every time that I write sine to an even power. Okay, so let's just write sine. Obviously, squared would be kind of pointless. All right, let's go sine the fourth of x. We can rewrite that as sine squared x times sine squared x, or that, right? Okay. If I have sine to the 6x, I can rewrite that as sine squared times sine squared times sine squared, right? Or sine squared x to the third. Does that make sense? Power to a power, you multiply, that's going to equal my 6, right? If I go sine to the 8, that would be sine squared to the fourth, right? So if I have, let's say, sine, I'm just going to use a capital E here for even, of x. That's going to be rewritten as sine squared x raised to the even power divided by 2. On it, you guys see that pattern existing there. Which then, here's the thing with that. If I have sine squared x squared, that's not too bad to manipulate. We're actually going to do that one here in a moment. Sine to the 6x, that wouldn't be too bad either. Because then when I FOIL, basically what's going to happen, let's kind of think about this. If I'm going to take sine squared times sine squared, I'm going to take that red expression, 1 minus cosine 2x times 2, and multiply it by itself twice, right? Well, then that means my numerators, because it's a binomial up there, my numerators are going to need FOIL, right? Well, if I do sine squared x to the third, then I would have that red fraction 3 times, right? Therefore, I have to FOIL twice, and then get that trinomial and multiply that trinomial by a binomial, okay? So I've got that distributive property happening several more times. Sine to the fourth, obviously, then is going to be, or sine squared to the fourth, sine to the eighth total, is going to be even more iterations of that multiplication, more iterations of distributing and FOILing, okay? The further we go along with that, the larger those exponents get, the more tedious that becomes. And then the more tedious that becomes, you might want to be looking for, like, alternative routes. You could start incorporating the binomial expansion process that you guys talked about in Algebra 2. You guys remember doing that? remember Pascal's triangle? Okay. Where we put the 1 up top and then the 2 1s underneath that on the side, kind of like a triangle. And then we go 1 3 1, or sorry, 1 2 1, 1 3 3 1, 1 4 6 4 1, right? And that gave us the coefficients of the expansion. And then if we look at the power we're interested in, we can kind of alter the powers of our terms in descending order, and then ultimately ascending order as well. But that's the binomial expansion process that might be incorporated the higher you get with your exercise. Okay. Now, I'm not going to ask you to do that, but that is, I think, an insight of this course and other courses. The more detail, the more in depth you get, you start bringing to the surface more and more math that you've used in the past to address your current situation. Let's go ahead and kind of see where this came from, okay? And it's not really all that hard to see where this came from. If we have, because there's a sine squared and a cosine of 2x incorporated inside that relationship, so I'm going to start with cosine of, let's just go 2 theta. If you remember cosine of 2 theta, one of the versions of that double angle was 1 minus 2 sine squared of theta. Remember that? Okay. Now, what is nice about this relationship here in developing these formulas is that that's cosine of the first, this is sine squared. If I solve for sine squared, it then gives me a form to reduce the power of 2 to a power of 1. So that's what we're going to do here. That's how these are formulated. I'm going to take cosine 2 theta. I'll subtract 1 from both sides. So it looks like this. And we'll divide both sides by -2, right? So divide both sides by -2. Tablet died. There we go. That'd be a negative. That'd become a positive. We have it over 2. That's going to give me sine squared. Is that okay with everybody? Okay. Well, a lot of times I don't like to write it that way. You're not going to see that +1 at the end. You'll see the 1 out here in front. And there's our power reducing formula for sine squared. Okay. Both of these are actually going to, when you have sine squared or cosine squared, it's going to reduce down to a formula that incorporates cosine only. Because the other format of cosine 2 theta that is of a benefit here is this one, where we go 2 cosine squared theta minus 1. If I add 1 to both sides and divide both sides by 2, I get that. So these are my 2 power reducing formulas for sine squared and cosine squared. I don't know how many you see in your homework, but what's the trig ratio that we haven't talked about yet? Tangent squared, right? Tangent squared would be sine squared over cosine squared, right? Well, sine squared is 1 minus cosine of 2 theta over 2, divided by cosine squared is 1 plus cosine 2 theta over 2. What's going to happen because of those 2's here being the same? They're going to cancel. That's because we're multiplying by reciprocals, right? And you're left with just 1 minus cosine of 2 theta over 1 plus cosine of 2 theta to theta. And that then is your tangent squared power reducing formula. You notice that no matter which trig ratio I start with, squared, it's always going to be rewritten down in terms of cosine. Okay? The way I remember these, and again, I know it's maybe not the best logic because we've used this before. It might get confusing, but those two formats, sine squared and cosine squared, the power reducing forms, are almost identical, right? Okay. The only thing that's different is that sign right there. So what I always do is I remember that sign is a negative, has an n in it. Negative has an n in it, so sign has an n in it. So I know that one's going to be the minus sign. Just the way I remember it. Ultimately, guys, maybe before the last class this, years ago, before Rhodes made the offer for college credit, stuff like that, when I thought this said just advanced math, I made my students learn all these things. I never gave them reference sheets. Okay. I started to start giving them reference sheets maybe the fourth or fifth year I was teaching them stuff, but my reference sheets were really vague, meaning that I gave them maybe the 1 minus cosine 2 theta over 2, but I didn't give them the sine squared theta. Does that make sense? So I gave them half the formula. Or maybe I gave them the whole formula, but I took out the theta and the 2 theta. And so they had to remember components of it, right? Okay. Rhodes says that we're just going to give you the reference sheet, which is fine. Okay, I don't have an issue with that. Because to be honest with you, when you guys are using these reference sheets, when you guys use this stuff for a intended purpose outside of this class, maybe in college, maybe in the workforce, whatever you're going into that might use trigonometry, you're probably going to have the ability to reference something to make sure that you're doing it correctly, right? Okay. Which is, I mean, some fields have it now, some fields don't. My sister's a pharmacist. I don't know if I've told you this before, but she texted me the other day, and she says, some of the people I work with blow my mind that they were able to graduate high school and get a college degree. She said, I had to tell a nurse that 1,000 divided by 100 was 10. Would you really hate to have that nurse dosing medicine to you? Yeah, because she couldn't do that math. It would be nice, obviously, I think in the medical, you get your diploma, you get your degree, I think they're assuming that you can do powers of 10 division. You don't have that reference, okay? But there are fields, obviously, where you can use references. You have time to do that. Other fields, thinking on the fly, maybe an ER nurse or something like that, you don't have time to reference stuff, okay? But obviously, I think, obviously, an ER nurse is not doing trigonometry on somebody.
Oh, you never know.
And if they are, they should probably be admitted themselves. But the questions that you guys saw in your homework then that are targeting these formulas are things like, I'm going to do 2 or 3 of these with you. Things like sine to the 4th x. Okay? So, like Derek said earlier, so does that mean we can just rewrite this as sine squared x, that quantity squared? And that's fine. Okay? Or, if you guys want to write it as sine squared x times sine squared x, like that, that's fine. Either one of those is fine. My voice has been cutting in and out this week. I don't know what's going on. Major changes. I can't wait. So, we can do that, and now we've got to make the substitution, right? So if I was doing it this way, I would go 1, now sine is 1 minus cosine of 2x all over 2, and then squared. And I think probably maybe the first couple times you do these, most people are probably actually going to rewrite that as 1 minus cosine 2x over 2 times 1 minus cosine of 2x over 2. You may be a person that does that, may not be. But if I do it that way, isn't that exactly what that would have been? Okay, so eventually you get to that statement regardless if you would have written it down first or not. So now when I look at that, here's what we see is that we're going to multiply those numerators. Well, those numerators, 1 minus cosine 2x, 1 minus cosine 2x, those are binomials, right? So you have to FOIL that. Now the nice thing is that they are the same binomial, okay? So we've got the a minus b quantity squared idea, where I could square the first term, Square the last term, multiply these two things together, and then double them, right? So it gives me that. So I can use that technique here. So 1 times 1 would give me 1, right? Okay. Multiply these together. O and I are going to eventually give you negative 2 cosine of 2x. And then last times last will give me cosine squared of 2x. Denominator times denominator is going to give me a 4, right? Okay. So you can write it all over 4. What I prefer to do is actually just factor that 1/4 out. I'd rather look at this trinomial here without a denominator. It's my personal preference. Okay. So what happened? We had a sine squared. We got rid of both of those, but now one showed up. Cosine squared. So that's still a problem. Okay. So we make another substitution. Okay. Now when you do these, so we're just doing to the fourth here. Sine of x to the fourth. When you do higher powers, that cosine squared is going to be a higher power. Does that make sense? And it just makes you do more iterations of what we're doing right now. We're going to have to go and substitute this. Okay? The higher this power here is, the more substitution you're going to have to do then. Okay? Or more kind of grabbing this one off here, substituting the power reducing formula, and then manipulating, and then eventually you'll have another one that you have to power reduce, and you keep doing that until they all disappear. Okay? So substituting that one there. Okay, I'm going to write everything else the same. 1/4 be 1 minus 2 cosine 2x. Now it's going to be plus. Now I got to rewrite cosine squared 2x. Okay? Now think about your power reducing formula. I'm going to write it. Let's write it right here real quick. Cosine of x. Cosine squared of x was equal to 1 plus cosine of 2x over 2, right? Looking at that setup there, and that formula, this x and that's 2x. What's the relationship between those two things? They're what to one another? Yeah, they're a multiple. This is a multiple of 2, right? Okay. So if this one was cosine squared of a, this one would be 2a, right? If this was r, it'd be 2r. If it was 30, it would be 60, right? But if it was 60, it'd be 120, correct? So what if this was 2x? What would that one be? It'd be 4x, right? That kind of makes sense to everybody? There's a 1 to 3 relationship there. So that's what I'm saying here, is that when I cosine squared 2x, usually, and we first set out this problem, it was sine squared of just x. So that's why this became a 2x. But now it's in a cosine, so it's going to become 4x. So you just got to be careful with that as you're doing this. So 1 plus cosine of 4x all over 2. Okay? Now I like to, like I said, I don't like looking at this binomial over 2. So I'm going to factor that 1/2 out. Just rewrite it this way. So 1 plus cosine of 4x over 2, is that the same thing as 1/2 plus 1/2 cosine of 4x? Does that give me the same thing I was looking for? And the reason I do that is for my next step. What do you see right here and right there? You add those together, can't you? 1/2 plus 1 is 3/2 minus then 2 cosine 2x plus then 1/2 cosine 4x. And I mean, I think WebAssembly would accept that. That would be fine. But we can go one step further. We can distribute that 1/4 back through and make this 3/8 minus 1/2 cosine of 2x plus then 1/8 cosine of 4x. And that then should be, and we're going to double check with the graph here, that should be the same thing as sine to the 4th times, or of x, sine to the 4th of x. So, like, where would this be beneficial? So, what if they said, like, here's an expression. Here's sine of, let's say, 30 degrees. They say sine of 30 times sine of 30 times sine of 30 times sine of 30. That'd be sine to the 4th of 30, right? I can either go for the unit circle and evaluate that, and take 1/2 times 1/2 times 1/2 times 1/2 and get 1/16, right? Or I could go to the unit circle and say, okay, what then is the cosine of 60, radical 3/2? Okay. What is the cosine then of 4x? So 120, right? Figure out the cosine of 120 is, so that's what, negative 1/2. And I can plug in 3/8 minus 1/2 times radical 3/2 plus 1/8 times negative 1/2, and that should give me still 1/16. Does that kind of make sense? Okay. I don't know if that obviously using 30 there, that's not really a benefit. Much longer process, but it should still pan out and work. Okay. Maybe we'll, instead of talking through that, maybe I'll write down that algebra here in a moment. All right. So what we're looking at then, if we want to look sine to the 4th of x, looks like that. Hopefully it makes sense why it's always positive, right? Okay, you can't take a number, square it, and then square that and ever get anything negative. We just came up with 3/8 minus 1/2 cosine of 2x plus 1/8 cosine of 4x, and it gives me the exact same thing. Okay. So algebraically, if you weren't checking with a graphing tool, okay, but you had maybe like a TI-30 or something, one of those red calculators up there, you could still do this, but now you just have to use specific values. So I said, what if x was 30? Okay, so we'd have sine of 30 raised to the 4th power, right? Sine of 30 is 1/2, right? So we'd have 1/2 to the 4th power, power to a power rule, so that's 1 to the 4th over 2 to the 4th, which is 1/16, right? Let's see if using x to be 30, I get the same information from here. I get 3/8 minus 1/2. Now cosine of 2x. So 2x would be 60, right? So cosine of 60, I think I misspoke earlier. Cosine of 60 is what? 1/2. Put that in. And then plus 1/8 cosine of 4x. Well, 4x would be 120, right? What's the cosine of 120? Negative 1/2, right? Let's add these things together. I got 3/8 minus a 4th minus 16th, right? Okay. 3/8 minus a 4th. What's 3/8 minus a 4th? 1/8, right? Okay. 1/8 minus a 16th is a 16th. Okay. That proved to us. Now, obviously, that's just one value, x being 30. If you did it with 45, if you did it with 60, if you did it with 15, we know what those ordered pairs are off the unit circle. We have the ability to find them. We can justify that. Okay. To be honest with you guys, it doesn't matter what x is. I use 30 because we need a unit circle, but if you plug in 22.4 and just use that as x through both those, you should end up with the same results in both of them. Prove to you that you've done things correctly. Okay? You will see, I think on your homework, they ask something, they start to kind of put them together, meaning they ask for it starts with a sine squared of x, and then a cosine squared of x. If we do that, so this is actually a pretty easy problem because 1 minus cosine of 2x over 2 is sine squared. 1 plus cosine of 2x over 2 is cosine squared. If I multiply those together, what do you have up there in the numerator? What are these things? Conjugates, right? So O and I are cancel out, leaves me 1 minus cosine squared of 2x all over 4. So I'm going to write it all over 4 as that, 1/4 of that. And now I've got some options, and there's nothing, either option is fine. Okay? Last class decided that this thing here we could rewrite as cosine squared, right? We have a power reducing for that, so we can write 1 minus. Now it'd be 1 plus cosine of what? If this is 2x, when I use the power reducing, it becomes 4x. It doubles it. And that would be all over 2, so I'm going to put that all over 2 kind of out front here. So it's 1 minus that stuff. In now, we go 1/4. We've got 1 minus a half cosine 4x. What's 1 minus a half? A half. So 1/4, 1/2 minus a half cosine of 4x. Okay, so you can do one of two things. You can distribute the 1/4 if you want to, so 1/8 minus 1/8 cosine 4x. Sometimes, I don't know about the feedback on what was signed, they might write that as 1/8 times the quantity of 1 minus cosine 4x. Either way is fine. Okay? I, however, think that is actually, even though it's a direct substitution of cosine squared, I think that's a longer process than maybe what we could do. And because of this negative sign here, it's negative 1/2, some people are going to mess up that sign right there eventually. Okay? So there's a way to avoid that. What is 1 minus cosine squared the same as? Sine squared, right? So we could have, I'm not saying that this is the way you have to do it, but you could have rewritten this as 1/4 of sine squared 2x. That's what 1 minus cosine squared 2x is, right? And now, sine squared 2x, well, that's 1 plus cosine of, no idea what just happened. All that stuff just went weird. So this was 1/4. So sine squared of 2x. Okay, so that sine squared turns into 1 plus cosine. We double this 2x, right? So it's 4x here, all over 2. Now if I multiply, if I distribute the 1 to this stuff here, then the numerator would be 1 times 1, which is 1. 1 times cosine, which is cosine 4x. And then I have 4 times 2 on the bottom, which would be 8, right? Does that thing turn directly into that? And it bypasses a little bit of that algebra, right? Okay. And that's the thing we kind of talked about last period is, guys, you might be uncertain. Is this the right substitution to make? Most of the time, as long as it's a valid substitution, you're probably going to arrive at your answer eventually. Okay? Making a substitution one way or the other might, doing that first one, we made the substitution of cosine squared. okay? And it took a little bit more algebra, right? We come back, we make the substitution of sine squared, and it cleans things up, makes it a little bit easier. When you're first doing these and being exposed to them for the first time, you might not see those things right away. And you might just say, okay, 1 minus cosine squared, power reducing formula, let's put cosine squared in there as 1 plus cosine of 4x over 2, and you work through the algebra. That's fine. But the more and more and more you see them, the more you might develop relationships that I know that 1 minus cosine squared is going to be sine squared, and that's probably going to be maybe more kind of likable algebra for us. Okay. We talked this idea right here, and I got the equation over there. But if I go 2x plus 3 equals 12, there's a lot of different ways we can do that problem. Okay, lots of different ways. The most efficient way is probably do what? Subtract 3 and then divide by 2, right? You can do that. Okay, and then that's going to give you the answer. So every time that we do one of these identity problems, there's going to be an efficient way. There's not always a right way. If I added 7 to both sides, would that be okay? So I'd have 2x plus 10 equals 19. Then subtract 10 from both sides. Do I still get 2x equals 9 eventually? Yeah. Okay. So, I mean, obviously, we all know at this point that adding 7 to both sides is inefficient. It's stupid. Nobody would do it, right? But because of our unfamiliarity with identities, maybe you don't know what's appropriate and not appropriate right away. Make a substitution that you know is true, that you're allowed to do, and it's perfectly fine. I'm going to venture to say that nobody would have done this on this equation. Nobody would have taken out a 2 and written this as x plus 3 halves equals 12. I think that's actually a pretty efficient way of doing it, because now I can take x plus 3 halves is equal to 6. Okay, that is 12 halves, right? So 12 halves minus 3 halves is 9 halves. So I can solve it that way, right? Not many people are going to do that, but that's the idea that we start to see and realize that it's a potential process, okay? Now, as we work through equations, if that plus 3 would have been a plus 4 or a plus 6 or a plus 8, if it was an even number, absolutely that's the route I'm going to go. Does that make sense? Okay? Because I think that's a little bit easier. I think that's using your algebra skills to your advantage. Okay? Now, as you guys work through some of this stuff, so let's say I'm just going to write down real quick that first one we did was sine to the 4th x. We came up with sine to the 4th x to be 1/8 minus 1/2 cosine of 2x plus 1. Actually, was this 1/8 here? No, that was 1/2. This is 1/8 cosine of 4x. Okay, is that correct? 3/8, yeah. Okay. So what if they asked me to find sine to the 5th of x? Is that the same thing as sine to the 4th of x times sine to the 1st of x? And I know sine to the 4th is that, right? Can I just multiply by sine x? That makes sense to everybody? So what it would end up giving me is 3/8 sine x minus 12 cosine 2x sine x plus 1/8 cosine 4x sine x. Distribute that sine through. So that's kind of the approach that you would use. You know, we talked about the approach if your power was always even, right? So if it was an odd power, you basically evaluate the even power that's below it, figure out what that is, and just distribute that either sine or cosine back through that even power expansion. Is that okay? All right, so on the 7-3, day 2 assignment, guys, I'm leaving that up tomorrow morning. Someone in the last period asked if I would put some similar exercises on there. So I did that, meaning that there's, instead of 3 attempts, there's 5 attempts now. Not that there's extra problems to do. So if you need more time on that, you have that. Tomorrow, first thing, we're going to jump right into trigonometric equations tomorrow. Okay? We'll start off, so trig equations are things that kind of categorize themselves. They group, it's just like any other type of equation. You know, linear equations, there's, you know, the way they show up, we might have x's on both sides. We might have just x's on one side. We might have to distribute on one side or distribute on both sides. So the structures kind of tell me what kind of group or category to put them in, right? Tomorrow we're going to start with the simplest category, okay? And then kind of build on that as we move forward. We're going to rely a little bit on our algebra. We're going to have to do some factoring tomorrow, okay? Might have to use P/Q a little bit eventually. Quadratic formula, that kind of stuff. Okay? So that's the plan. And we'll probably spend the rest of this week and most of next week on trig equations. Okay? And then towards the end of next week, it's okay. Towards the end of next week, have a test over chapter